So today we have Andrey Soldatenkov, who is going to talk about absolute Hodge classes and the Mumford Tate conjecture for hyperkähler manifolds. So Andrey, please.
Yes, thank you very much for the invitation. So I, in general, study hyperkähler geometry, but recently I did some work that will probably be interesting for the participants of this seminar. So it is somehow related to the Hodge conjecture and to some other conjecture, which is called the Mumford Tate conjecture. I'll try to give you an idea. Probably I will not go into details of the proofs, but I'll just try to explain in general idea of what I was studying. So let me first recall the notion of an absolute Hodge class or an absolute Hodge cycle. So let's say we have a complex projective manifold, so smooth projective variety over C. Then we have the algebraic Deligne complex. And we can compute Deligne cohomology of X, which is just the hypercohomology of this complex. But then we can also compare this with other cohomology theories, and there are some natural isomorphisms. So from here we can pass to the corresponding complex analytic variety using Gaga, and this will be isomorphic to the hypercohomology of the corresponding analytic Deligne complex, which is a resolution of the constant sheaf. As we know, so this is a resolution of the constant sheaf with fiber C. And so here we get just the ordinary singular cohomology of the corresponding complex analytic space. Yeah, so this is the natural comparison isomorphism. And also we have, well, what can we say? We have a the Hodge to Deligne spectral sequence that computes the cohomology of our manifold, the singular cohomology of our manifold in terms of the cohomology groups of the differential forms. Okay, so so this vector space HK Deligne, which is isomorphic to the singular cohomology, let me just briefly denote this vector space by HK. And so what kind of structures do we have on this vector space? So this is a C vector space. Well, first of all, we have the filtration induced by this Hodge to Deligne spectral sequence. It's called the Hodge filtration. It can be described as follows. We consider our Deligne complex and we truncate it in degree P. So we replace all terms in degree less than P by zeros, and then this will be a subcomplex here. And we have the corresponding map on the hypercohomology, which will give us a subspace, which I denote by FP. So this is the image of the corresponding morphism. Like this. And also on this, so this Hodge filtration, it comes somehow from the right-hand side of the equality above. It is somehow expressed in terms of the Deligne complex. But on the left-hand side, we have the singular cohomology, and the singular cohomology actually has some additional structure also. It's the Q structure, the structure of the rational vector space. So this complex vector space is a complexification of the rational cohomology. So these two things, they build up the Hodge structure. So we have the Hodge decomposition. And now, yeah, so this Hodge structure is polarized, and now we call a class, a cohomology class is called a Hodge cycle. If it is if it is of degree 2p for some p, and it lies in the component fp of the Hodge filtration. And also it is rational, well, up to some Tate twist. So this is usually called the Hodge cycle. Well, why is it a cycle? Because naturally such, well, it's not a cycle, it's a cohomology class, but this is a standard terminology. And the reason is that such Hodge cycles, they really come if we have the real cycles, namely subvarieties or subvarieties in our manifold. So if we have a subvariety y of codimension p, then its fundamental class is a Hodge cycle. And the Hodge conjecture implies that all Hodge cycles are linear combinations of such fundamental classes of subvarieties with rational coefficients. Yeah, so okay, so what, yeah, so that's of course not known even for the simple examples like abelian varieties, for example. So what else does this conjecture imply? Well, actually, we can do the following thing. So we have our manifold over C, an algebraic variety over C, and now we can apply some automorphism of this field of complex numbers. Namely, we can take the equations that define X in the projective space and apply to this to the coefficients of this equation some automorphism. So let's take an automorphism of C over Q. So this in terms of so scheme theoretically, this as a result of this application of this automorphism to the coefficients is just the base change along the morphism from spec C to spec C, yeah, which is given by this automorphism sigma, and then we get this conjugate variety X sigma. It's also a complex projective manifold, and then we can again compute its cohomology. So we can write HK, the RAM of X sigma, and again we know that it will be isomorphic to the singular cohomology of the corresponding complex analytic space. On the other hand, since this was obtained by base change, so there is also the base change formula for the Deligne cohomology. So this will be just the same vector space, but whose structure of a complex vector space is obtained somehow is twisted by this automorphism. Yeah. So this is essentially just as a set. It is the same thing as HK Deligne of X. Okay, so and now what happens to the Hodge cycles when we do this? Or suppose we had some Hodge cycle on X and we apply this automorphism, and then does this Hodge cycle remain a Hodge cycle? So here is the definition. So if this Hodge somehow, if some cohomology class remains a Hodge cycle for all automorphism sigma, then it is called an absolute Hodge cycle. So we can take some element in the corresponding in FP, H2P, and so I want to call this element an absolute Hodge cycle. If it will be contained in the corresponding rational subspace for all conjugate varieties X sigma. So for any sigma. So I will denote this space of absolute Hodge cycles like this. It's a Q subspace of absolute Hodge cycles. And so what does the Hodge conjecture tell us? In fact, if we believe in Hodge conjectures, then all these Hodge cycles, they come from subvarieties. But then if a Hodge cycle comes from a subvariety, and we apply this conjugation procedure, then we can also conjugate the subvariety. And so then it is clear that the cycle remains Hodge. And so for any subvariety Y in X, this fundamental class will be an absolute Hodge cycle. So the Hodge conjecture implies, in particular, that all Hodge cycles are absolute. All right, so yeah, so that's so this statement is some part of the Hodge conjecture. All Hodge cycles are absolute, and in fact, we know more about this statement than about the Hodge conjecture itself. Deligne proved, I believe, in 1982, that this statement is true at least for abelian varieties. So this is the theorem. So all Hodge cycles on A are absolute. All right. Well, when we work with this notion, it's also useful to introduce some category of motifs to deal with this kind of questions. This was also done by Deligne. Let me just briefly recall this. It's very convenient to express everything in terms of motifs because, yeah, if we want to study the question of whether the cycles on some algebraic variety are absolute or not, then well, it's useful to work with its motif, which somehow was some sort of motif, which is called Deligne motif. So let me recall briefly the notion of a Deligne motif. Motifs are defined usually in terms of correspondences, and correspondences are some cycles on the product of two varieties. So in our situation, we will use the absolute Hodge cycles as for correspondences. So the space of correspondences of degree d from x to y. So again, x, y are smooth projective varieties over C. And the space of correspondences is just the space of absolute Hodge cycles of a degree twice the dimension of x plus d absolute on the product x times y. So you can think of them as the graphs of maps, or some generalization of the notion of a graph of the graph of a map. And there is, as usual, the composition of correspondences is defined in the usual way. So let me recall. So I have correspondences of degree d1 from x to y, and correspondences of degree d2 from y to z. And I get a correspondence of degree d1 plus d2 from x to z. So how do I do this? I take a pair of correspondences and I map it to the composition, which is obtained as follows. I look at the triple product x, y, z, and then I pull back one correspondence from one side, take the cup product with the pullback of the other correspondence from the other side, and then I push forward to the to xz. Okay, so then using this, we define the category of Deligne motifs. Its objects are triples x, e, n, where x is smooth projective as before, smooth projective variety. P is correspondence of degree 0 from x to x. So P is essentially an endomorphism of x of degree 0, which is also a projector, so it is idempotent. And n is some integer. Well, I'm a bit sloppy here, so when I'm talking about motifs, actually, strictly speaking, I should allow x to be disconnected to have several connected components, and then n is not an integer, it's a map from the set of connected components to the integer. So it's an integer for each connected component, but let me just ignore these technicalities for the purpose of this talk. I think it's not so important to give all the definitions completely rigorously. So, okay, so these are objects. Well, if you have seen the Chow motifs, then this is very familiar, except that you replace Chow groups by the spaces of absolute Hodge cycles. And then you also define the morphisms from one motif to the other. So these are correspondences of some degree from x to y, but also so they are pre-composed with the projector P and post-composed with the projector Q. So let's, if we have a variety, let's denote its motif by M of x. So the motif of x is the following triple. We take x, then the projector is a correspondence from x to x, so it should be some absolute Hodge cycle on the product x times x, and we take the class of the diagonal in x times x. And this n is 0. All right, so this is the motif of variety x. We have this category. So what can we say about it? It's actually a very good category. It has so let's denote the category by curly MD, the category of Deligne motifs. It has the direct sum, the tensor product, it has a unit, it has duality. So actually it is a semi-simple neutral Tonican category. Which means essentially that it is equivalent to the category of representations of some pro-algebraic group. So you can think of these motifs as of some sort of representations of some group. This formalism is quite convenient. Okay, so now how do I want to use it? Well, let's look at this subcategory inside this MD generated by all abelian varieties. So I take motifs of all abelian varieties. Subcategory generated by M of A for all abelian varieties. Then this is also, well, by a subcategory generated by this, I mean the smallest full Tonican subcategory. We can say that if our variety, so if we have computed a motif of our variety, and it turns out that this motif is contained in this subcategory, then we conclude from Deligne's theorem, this is essentially the same theorem of Deligne, we conclude that all Hodge cycles on our variety are absolute. Yeah, so you see somehow if the motif of X is contained in this subcategory, then this means that we have constructed some correspondence between this X and essentially some abelian variety, and the correspondence is given by some absolute Hodge cycles. Then we map our Hodge cycles from X to this abelian variety using this correspondence, and on the abelian variety, we know by Deligne's theorem that the Hodge cycles are all absolute. And then somehow this, then we can transfer back this absolute Hodge cycles to X, so we get back the cycles that we had, and somehow we deduce that the cycles on X are also absolute. Yeah, so, well, how do we prove that some motif of something is abelian? Usually one can apply some geometric constructions. Well, one can prove for some simple varieties, for example, for the curves, the motifs are abelian. For K3 surfaces, we know it was known and it was proved, I guess, by Deligne, that the motifs are abelian also. And starting from these basic examples, we can produce more examples of varieties with abelian motifs by using some geometric constructions. For example, assume that we have some morphism, dominant morphism. From X to Y, then you can prove that the motif of Y is a submotif in the motif of X, where the pullback. And then if we know that the motif of X was abelian, Yeah, so I call motifs that are contained in this subcategory M curly M abelian D. I call them abelian motifs. Okay, so if M of X was abelian, then it follows that M of Y is also abelian. And then I can deduce that all Hodge cycles on Y are absolute and some other things. Another example is the blow-up. So if I, if I have a subvariety inside X, and and I know that the motif of X and the motif of Y are abelian, then the motif of the blow-up of X along Y is also abelian. It's because you can express the motif of the blow-up similarly to what you have in cohomology. So the motif of the blow-up will be just the direct sum of the motif of X and several copies of Tate twists of the motif of Y. Okay, so this is nice. So now I want to try to apply this to the varieties I'm interested in. So I study hyperkähler manifolds. Let me briefly recall, because probably people are not familiar with this notion. Let me talk about projective hyperkähler manifolds. So what is a hyperkähler manifold? Today, this will mean the following. In general, there is a more general notion in differential geometry, but today, so for me, a hyperkähler manifold I'll briefly write HK. X is hyperkähler if it is first simply connected. So X, sorry, so let me write this again. So I assume as before that X is a complex projective variety, first of all. So X is a smooth projective variety over C, just as before. Also, it is simply connected. And the space of holomorphic two forms on X is spanned by a symplectic form. So this is essentially just an algebraic symplectic manifold, which has a unique symplectic form up to rescaling by a complex number. So what are the examples? The most well-known example is a K3 surface. So if S is a surface, again, so by a surface, I mean today a smooth projective surface over C. Then it is hyperkähler if and only if it is a K3 surface. So I recall what it is. So this means that the canonical bundle of S is trivial, and it has no holomorphic one form, so no homology of the structure sheaf in degree 1. So that's a K3 surface. An example of a K3 surface is a quartic hypersurface in P3. So a hypersurface of degree 4 in P3 by adjunction formula, it is clear that its canonical bundle is trivial, and then you can check also that the other condition is satisfied by Lefschetz. So that is a K3 surface. Now, starting from a K3 surface, we can produce more examples of hyperkähler manifolds. So there is a series of examples in each even dimension. There is the manifold, the Hilbert scheme of points on a K3 surface. Yeah, so its dimension is 2n, and x is hyperkähler. Well, we consider just, so what is this Hilbert scheme? It's just the usual Hilbert scheme in the sense of algebraic geometry. Yeah, so strictly speaking, it's a Hilbert scheme of subschemes of finite length, of length n. Well, the easiest example is when n equals 2. Then you can describe
this
this very.
This is the smooth, this x.
Yes, so this Hilbert scheme will be smooth, as is smooth, and the Hilbert scheme will be smooth for any surface, actually, not only for K3 surface, but for any surface, the Hilbert scheme of points is smooth. Yes.
I see.
So the non-smooth thing is just a symmetric product of somehow of self-product of this surface, and then the Hilbert scheme will be a frequent resolution of this symmetric product. So, for example, let's look at the example of n equals 2. So we take s times x, and then we can just take the quotient by the action of the involution that permutes the two factors, and then we get the symmetric square of s. And this symmetric square, it admits a resolution. So how to get a resolution? We can first blow up the diagonal in this s times s. Then the action of the involution that permutes the two factors will extend to the blow up, but then the fixed locus of this action will be the exceptional divisor, and then it will act along the exceptional divisor as a reflection, and then for such action the quotient is actually smooth, and the quotient is the Hilbert scheme of 2 points on S, and this will be a minimal frequent resolution of the symmetric square. Okay, so this is the example. This is one series of examples of hyperkähler manifolds. So yeah, I must admit that there is a series, but then we can also apply deformation theory to these hyperkähler manifolds. So we can deform them as just as complex varieties. And not every hyperkähler manifold that you get by deformation is isomorphic to the Hilbert scheme. So there will be lots of deformations, even projective deformations, that are not Hilbert schemes anymore. For example, so what is the other way to obtain this deformation? So we can consider more generally a moduli space of semi-stable sheaves with some fixed numerical invariance on a K3 surface S with respect to some polarization. And then, well, this moduli space is not always smooth, but sometimes it is smooth, like in this previous example of the Hilbert scheme. The Hilbert scheme is a special case of this. The Hilbert scheme is a moduli space of ideal sheaves of endpoints. But there are some other cases when the moduli space will be smooth, and then if X is smooth, it is hyperkähler, and it is a deformation of the Hilbert scheme for some n. So these moduli spaces give us examples of hyperkähler manifolds in the same deformation class. There are also nice geometric constructions. There are lots of them actually. I just want to mention one simplest geometric construction that gives you a hyperkähler manifold. So suppose we have a cubic in P5, a cubic fourfold.
So in this previous example, the sheaves are coherent or just
coherent sheaves. Sorry, semi-stable coherent sheaves. Yes. Right. So a cubic fourfold. A cubic fourfold contains lines, so you can easily check that there are lines on a smooth. So let me write a smooth cubic fourfold. There are lines on any cubic fourfold, I guess, but I want only smooth. And the variety of lines, it's called the Fano variety. So X, the Fano variety of lines on Z. It turns out to be four-dimensional, and it turns out that this Fano variety of lines is a hyperkähler manifold. And actually, it is a deformation of the Hilbert scheme of 2 points on a K3 surface. So this, that is more, that's kind of a geometric construction. So there are other geometric constructions which I won't mention today because they're more complicated. But actually, all these geometric constructions, the point is that they do not give us a new deformation class. So most of the constructions that come from geometry of hypersurfaces in PN, for example. So most of the constructions, they give hyperkähler manifolds that are deformations of Hilbert schemes of points on a K3 surface. But there are some other deformation classes known. So actually there is another infinite series of examples in any even dimension. They are obtained from abelian surface. If you start from an abelian surface, and you can try to do the same thing, you can consider the Hilbert scheme of points on an abelian surface. But this will not be hyperkähler because it is not simply connected. Recall that my hyperkähler manifolds were by definition simply connected. But I can take the Albanese map. There is the Albanese map from this Hilbert scheme. It's easy to describe. It takes the points, so that is the Hilbert scheme of n+1 points. So I take these n+1 points and I map them to the sum. So my abelian variety has the structure of an abelian group. So I take this sum of n+1 points, and that is a smooth fibration. So you can check that it's a smooth fibration, and it's a hyperkähler variety. So if I take the preimage of 0, for example, then this will be a smooth hyperkähler variety, which is called a generalized Kuma variety. So it is hyperkähler of dimension to n. And there are two more deformation classes known. So there are two exceptional examples. Due to O'Grady, so they are of dimension 6 and 10. They are usually denoted OG6 and OG10. Well, they are obtained in their construction is more complicated, but in some sense similar to what we did before. So you see, we consider these moduli spaces of sheaves, of coherent sheaves, with some fixed numerical invariance on a K3 surface. I said that these moduli spaces, they can be smooth, they can be singular sometimes. And sometimes you get singular moduli spaces, which you can resolve nicely. So they admit crescent resolutions sometimes. And then these singular moduli spaces, they give you some new deformation class of hyperkähler manifolds, which is called OG10. They are 10-dimensional. And similarly, on an abelian surface, you can also consider moduli spaces of sheaves, and sometimes they're singular, sometimes you can resolve their singularities, and they give some new deformation class, which is called OG6. Okay, so this is all, these are all examples that are known right now of hyperkähler manifolds. Okay, so what is the main result? I wanted to explain. The main result is the following. So I can prove that if you have two projective hyperkähler manifolds, sorry. So assume x1 and x2 are two hyperkähler manifolds, as before, projective always. But assume, so the second Betti number should be bigger than 3, and assume that they are deformation equivalent. But not equivalent. But not as projective manifolds, but just as complex varieties. That's important because somehow generic deformation of a hyperkähler manifold will not stay projective. And you can get some other projective manifold by deforming your original manifold, but you should pass through some non-projective somehow points in the moduli space to do this. Okay, and then I claim that the motif of x1 is abelian if and only if the motif of x2 is abelian. Yeah. So what does it give us? Why is it nice to have such a result? Well, actually, you can deduce from this that in all known cases, so the corollary motifs of hyperkähler manifolds of all known deformation types are abelian. So how do we prove this? Well, actually, so you see, the point is that in each deformation class, and I have listed all the deformation classes, essentially there are these two exceptional deformation classes, example 4, and there are two deformation classes in every even dimension. So examples 2 and 3.
When you are saying the deformation class, this is the analytic deformation class or
Yes,
algebraic?
yes. No, analytic, exactly. So that's the point. So it's an analytic deformation class, right? So you deform it as a Kähler manifold, to be precise. So you want the deformation to be Kähler, but you do not want it to be projective. And then there are only these examples. Inside the module.
I mean, the good thing of the theorem is that even so you pass from x1 to x2 by deforming to non-algebraic objects, still this
Yes,
abelian,
right.
the property of abelian being abelian is preserved.
Yes, exactly, yes. So that is the point. And then this means that to prove that the motifs are abelian and then to deduce that all Hodge classes are absolute, you need to find just one example in each deformation class of a manifold for which you can prove that its motif is abelian using some geometric construction. And you can do this. So these constructions were known already before. So let's just consider some examples. So for example, how do we prove using this theorem that any K3 surface, a projective K3 surface, I mean, has an abelian motif? So let's take a K3 surface. Yeah, so for example, this quartic in P3, I guess it's already interesting enough because it is not obvious. Well, okay, maybe for a hypersurface you can find some explicit way to prove that its motif is abelian, but there are some other examples of projective K3 surfaces. There are lots of them. So how to prove that the motif is abelian? So I just need to give you one K3 surface, one particular K3 surface with an abelian motif, and this is a Kume surface, obviously. So how do we construct a Kume surface? We start from an abelian surface. And then we do the following thing. So we can take this abelian surface and take its quotient by the involution, by the action of plus minus 1, by the action of Z2. So this will be singular, and this surface admits a resolution, which is a K3 surface. So this K3 surface will have 16 minus 1 curves as 0. So this is a Kume K3 surface. Or you can also first blow up the torsion points, the 2 torsion points. So there are 16 2 torsion points on your abelian surface. You can blow them up and then take the quotient of these by the involution. Yeah, so this will give you the same surface as 0. Now, so the motif of A is of course abelian. And then remember what I said about these abelian motifs. So if I blow up, a point in an abelian surface, the motif of the blow up will of course be again abelian, because the motif of the point is also abelian. So somehow the point is a 0-dimensional abelian variety, you may say. So the motif of this Y is abelian by this remark I mentioned before. But then this map is dominant, so it's dominant and generically finite, actually. So this already is enough to conclude that the motif of S0 is contained in the motif of Y. So it is also abelian. So the motif of S0 is abelian. And then you can apply this theorem and conclude that for all other K3 surfaces, the motifs are also abelian, because it is known that all K3 surfaces are deformation equivalent as complex surfaces. Yeah, okay. So that's one example. Well, you can also easily say what to do with the Hilbert schemes and their deformations. It's very similar. So I have already shown this diagram where you construct the Hilbert scheme of 2 points on a surface. So you can take the quotient of S times S by the involution, and then you can resolve it. You can get this Hilbert scheme of 2 points, or you can first blow up this S times S along the diagonal and then take the quotient. So now you see from the first example, we know that the motif of S times S is abelian because this property is preserved under taking products. So taking products of varieties corresponds to taking direct sums of their motifs. So, sorry, taking tensor products of their motifs. Since this DEM abelian D is a tensor subcategory, so this is closed under taking tensor products, and the motif of S times S is again abelian, then we blow it up along the diagonal. So the diagonal is also a K3 surface, so its motif is also abelian. So again, we conclude that the motif of Y is abelian. And then again, the quotient map to S2 is generically finite, so this motif of S2 will be embedded into the motif of Y. So it is again abelian. And then we apply the theorem and conclude that the motifs of all S2 type hyperkähler manifolds are abelian. S2 type means that it is a deformation of S2 as a complex manifold. And then you do similarly, you treat similarly all other families. So you always find some example of a hyperkähler variety in each deformation class with some explicit geometric construction, which essentially consists of some blowups and taking quotients, and then somehow deduce explicitly that the motif is abelian using this geometric construction. So I will not describe these geometric constructions now. I'd rather talk about this Mumford Tate conjecture. So this is another corollary of the theorem, that you can prove some cases of the Mumford Tate conjecture for all deformation classes of all known hyperkähler manifolds. Okay, so let me just briefly discuss this Mumford Tate conjecture in the end of my talk. So what is the Mumford Tate conjecture? Well, we started from this smooth projective variety over C, but actually any smooth projective variety over C, it is defined over some subfield finitely generated over Q. So we can find always some finitely generated subfield well, which means that just we take all the coefficients, polynomials that define X and generate the subfield over Q by these coefficients. And then so our X is smooth projective over this K. And then let's fix a prime number, L. So then we also have another cohomology theory. We have L-adic cohomology, which I will denote like this: HK et al. X. Then you take the base change to the algebraic closure of K. Then you compute L-adic cohomology some inverse limit of metal cohomologies with coefficients in ZL, and so this is the L-adic cohomology, and there is also a comparison theorem with the singular cohomology of the corresponding complex analytic space. This will be obtained from the usual singular cohomology just by taking the tensor product with QL. So let's denote this vector space. This is a QL vector space. So this QL vector space. Now, so there are again some additional structures on this vector space. On the left-hand side, we have the Galois group action. So let's denote by row the corresponding representation. So this is the Galois group. It goes to GL HKL. And let's take this Zariski closure of the image of this representation, denoted by GKL. So Zariski closure of the image of row. This will be some algebraic group over QL, and then let's take the identity component of this group. This will be GK0L. So the identity component of this GKL. So we have a subgroup in GL HKL in the in GL, some algebraic connected algebraic group inside the GL of this QL vector space. But then there is another connected algebraic group that acts naturally on this vector space. It's the Mumford Tate group. So recall that this on this side here, so this HK analytic tensor QL, so this HK analytic with rational coefficients, it has a Hodge structure. So there is the Mumford Tate group. Well, let me just recall. Maybe not everybody remembers what the Mumford Tate group is. So let's recall. So we have HK with complex coefficients is decomposed, as I have recalled already in the beginning, like this. And then there is C star action on this space.
Andrey, just to let you know, we have 2 or 5 minutes.
Okay. Okay. So yeah, let me then. Okay. So maybe let me not go into the details, and then let's just denote by the. Okay. So let me say that we consider this action the representation of C star, and then we take the smallest algebraic Q group, so the smallest algebraic group defined over Q, whose complexification contains the image of this representation. So we get the Mumford Tate group inside GL of HKXQ. Okay, then we can take the tensor product of this Mumford Tate group with QL, and we get an action on HKL, on this QL vector space. So we see this QL vector space HKL, so this one here, it has two natural, so there are two naturally defined algebraic groups acting on this space. And the Mumford Tate conjecture is that these two groups are actually equal. Sorry. So they're equal as subgroups in GLHKL. So this is not, this conjecture is not known even for abelian varieties, not known even for abelian varieties. Although it was known, so some cases of this conjecture were known for some hyperkähler manifolds. So Andrey proved in 96 that Mumford Tate conjecture for k equal to 2 and x any hyperkähler manifold. So yeah, so for any hyperkähler manifold, this was known for cohomology of degree 2. And now we can deduce as a corollary of the theorem that I told you that this Mumford Tate conjecture holds for all known deformation types of HK manifolds in all even degrees. So for all cohomology groups of all even degrees. All right, so yeah, I think let me stop here. So there's a proof of this uses that the motifs are abelian, and then somehow one has to know something else about the cohomology of hyperkähler manifolds, namely that there is some natural Lie algebra action, and then it is quite easy to deduce from the theorem that the Mumford Tate conjecture. So okay, thank you. I think I'll stop here.
Okay.